Well, hello and welcome to lesson 21-1 practice. We're on page 285. I thought I'd take a moment and kind of help guide some of those that are still struggling through lesson 21, kind of provide some assistance on the practice. So let's get started. Item 10 says find each unknown length and simplify your answer in radical form. So we're not giving decimals here. We're learning, hopefully, how to simplify these radicals. A radical, most of us refer to this symbol as a radical. We refer to it as a square root, but because we can have a cube root and a fourth root and so on, it's actually referred to as a radical. So as long as you know the connection between radical and square root, we're talking about the same thing. So we're going to, looks like we're going to be using the Pythagorean Theorem here because we are dealing with right triangles. And on A, we are given two measures on this triangle, so we can use the Pythagorean Theorem to find the third. Pythagorean Theorem is great for right triangles as long as we have two of the sides known. Now, one of the most important things we need to establish, and they kind of help us out here by telling us that this is B, or the length of this side is represented as B, is in the Pythagorean Theorem, A squared plus B squared equals C squared. A and B represent the length of legs, and C represents the length of the hypotenuse. So ask yourself, which of these measures is the hypotenuse? Well, it's always opposite of the right angle. Always, always, always. So 38 is going to be our hypotenuse, so we'll use that for C. And 27, we'll use it for A because they're telling us we're looking for B. So we'll say A squared, and we'll plug in 27 for A, plus B squared is equal to C squared, which we'll plug in 38 for C. Now take some time, work through squaring these and get down to B before playing through. Okay, so let me just establish something. And I notice oftentimes when I show this in class, people get a little hung up here because I go ahead and put the square root symbol back in this step. So this originally said B squared equals 715. And our goal is to find B, not B squared. So to get rid of the squared, we take the square root. So if B squared is 715, B equals the square root of 715. Now they told us to simplify our answer in the simplest radical form. And so we have to ask ourselves, is 715 simplest radical form? So here I'm going to suggest one of the easiest ways to simplify radical is find a perfect square factor of the number we're trying to simplify. So our perfect squares, starting with 1 squared, which is 1, 2 squared, 4, 3 squared, 9, 4 squared, 16, 5 squared, 25, 6 squared, 36, 7 squared, 49, 8 squared, 64, 9 squared, 81, and 10 squared, 100. Start with seeing if any of these are factors of the number we're trying to simplify. Potentially, the larger numbers we get into, we might have to go past 10 squared, but maybe even 11 squared, we'll add that 121. I've noticed 11 is often a common one. So see if any of these numbers are factors. And just to recall what a factor is, it means it's a number that can multiply by another whole number to give us the number we're trying to simplify. So did any of these numbers on any of these perfect squares divide into 715 evenly? The only one that did was 1, and that's because 1 is a factor of all numbers. So this is actually the simplest radical form for B, square root of 715. We are going to have to, as you get further along into mathematics, we're going to have to get more comfortable with the fact that that is an actual number in mathematics. Now, could we represent it as a decimal? Sure. But in order to write that decimal on this paper, we'd have to round it. So this, oftentimes in math, we like the most exact value. We don't want to round. We want to be as exact as possible. Now let's look at item B. Notice that they're now giving us a diagram of a rectangle. They've drawn a diagonal here, and that's what they're actually asking us to find. Find the length of the diagonal. But approach it a little bit differently because when we draw a diagonal in a rectangle, we actually create two right triangles. And if we have a right triangle, we can use the Pythagorean theorem to find a missing side, assuming we have two of the sides already. And now the two sides that we're given are the legs, 14 and 35, so that could be A or B, as long as we know that X we're finding is our hypotenuse. So let's get a different color here. 14 squared plus 35 squared is equal to, I guess we'll plug in X for C if you want to. So take a moment, get down to solving for X, and I'll jump back in and show you how to simplify our radical. So hopefully you got to the point where we found X is equal to the square root of 1,421. And I do want to say before I show you how to simplify the square root of 1,421, always check to see if this is a perfect square by simply putting in that in the calculator, square root of 1,421. Problem is, when you put the square root of 1,421 in the calculator, you get 37.6961. So it's not a perfect square. So I'm going to show you another method. Maybe if you don't recall your perfect squares, maybe that's a little bit of a challenge. So I'm going to show you another method here on B using something we call the factor tree. So maybe you can't figure out the perfect squares, maybe you don't recall those. Start by figuring out two factors of 1,421. Now, a lot of you might start with 2 and then go to 3 and go to 4 and go to 5 and go to 6. And if you just keep dividing 1,421, you'll notice that 7 is one of our first factors of 1,421, besides 1, of course. And 1,421 divided by 7 is 203. Well, 7 is a prime number. Its only factors are 7 and 1. So we're going to stop factoring right there at 7, but we're going to see if we can continue factoring 203 any further. Hopefully you remember this known as the factor tree. And so if you start taking 203 and dividing it by 2 and 3 and 4 and 5, you notice that one of its first factors besides 1 is 7 again. And 203 divided by 7 is 29. So if you notice, we can actually rewrite 1,421 as 7 squared times 29. Notice it's 7 times 7 times 29. And so we do have a perfect square factor of 1,429, 7 squared, which is actually 49. So we can rewrite the square root of 1,421 as square root of 1,421 as the square root of 7 squared times 29. Well, the square root of 7 squared is 7, and so we'll put that outside the square root or the radical. And because 29 is not a perfect square, we'll leave that under the square root or the radical. So x in its simplest radical form is 7 times the square root of 29. So a slightly different way to look at it. Notice we're still using the perfect square of 49, which is 7, but now more of a visual representation using the factor tree. Now, 10a and b gave us a nice warm-up into some of the ones I would encourage you to focus more on. Looking at right triangles in different contexts, not just a picture of a right triangle, find the missing side. But for example, in 11, it says find the area of a rectangular rug if the width of the rug is 13 feet. And so you might be asking, why are we dealing with a rectangular rug if we're dealing with right triangles? Well, look back at 10b. That's a rectangle. And when we draw a diagonal of a rectangle, we actually create two right triangles. So if we have a right triangle, we're looking to use the Pythagorean theorem. So the width of the rug is 13. No specification here. I just typically draw this up here with. You could have written it down here if you like. And the diagonal is 20. So we actually do have two measures of a right triangle. So we should be able to definitely find our length of the rectangle. And then, because area of a rectangle is length times width, we'll be able to multiply the length times the width to find the area of the rectangle. So as long as we know that 20 being the diagonal, that has to be C in the Pythagorean theorem. 13 could be A or B. So we'll have 13 squared plus B squared equals 20 squared. So take a moment, get it all the way down to finding b. So hopefully doing our proper order of operations here, we found that b equals the square root of 231. So I'm actually going to try to, notice I use the term try to use the factor tree to see if that can be simplified. So factors of 231, the lowest factor besides 1, of course, is 3. 3 times 77 is 231. Now 3 is prime, so we're going to stop there. 77 isn't, because I know that 11 times 7 is 77. But here's the problem, and a great distinction between this one and the other is our factors are all prime, and there's actually no perfect square factor of 231. So this is in simplest form. So they want us to, now that we know the length of this side is the square root of 231, they want us to find the area of the rug. So I'm going to teach you a little trick here, or just a little mathematic principle. If the width is 13, we'll multiply that by the length, square root of 231. When you have a number not underneath the radical and a number underneath the radical, and you're multiplying, just like you multiply 3 times x, these are considered unlike terms, you get 3x, you just simply push them together. We're going to do the same thing here. 13 times the square root of 231 is 13 times the square root of 231. We simply just push them together. And that is the area of the rug, which we measure area in squared feet. In this case, because we are dealing with feet. Now let's take a look at item 12. Which of the following is known as a Pythagorean triple? Be sure to go back to the check your understanding, item 5 on the previous page, to understand what a Pythagorean triple. It's a set of non-zero numbers that satisfy the Pythagorean theorem, such that a squared plus b squared does in fact equal c squared. Now, one thing I want to impress before we dive into this is your longest measurement of your set has to be your hypotenuse c, because assuming this is a Pythagorean triple, assuming these are sides of right triangles, the longest side has to be our hypotenuse. So in this case, of course, 6 will be c, 26 will be c, 25 will be c, and 41 will be c. So we're really just figuring out, do these three sides create a right triangle? Do they satisfy the Pythagorean theorem? For example, on A, does 3 squared plus 4 squared equal, I'm going to put a question mark there, does it equal 6 squared? So take a moment, figure out, does it in fact equal 3 squared plus 4 squared equals 6 squared? So 3 squared is 9, 4 squared is 16, and 6 squared is, I got ahead of myself here. 6 squared is 36, and 9 plus 16 does not equal 36. In fact, it equals 25, which I had up there. So A is not a Pythagorean triple. So now continue this pattern to see if these three values satisfy the Pythagorean theorem. Thus, they are called Pythagorean triples. So, simple concept, but of course we need to make sure we're doing this properly. Does 7 squared plus 25 squared equals 26 squared? Does that equal? Notice I put a question mark above the equal sign. No, it does not. Does 15 squared plus 21 squared equal 25 squared? No, it does not. So again, A, B, and C don't satisfy the Pythagorean theorem. Therefore, they're not Pythagorean triples. Therefore, they are not side lengths of right triangles. But item D, 9 squared plus 40 squared does in fact equal 41 squared. So what we're saying is we could actually have a right triangle with a leg that's 9, another leg that's 40, and the hypotenuse 41. I think it's good to put this back into context. Sure, we could just plug all these numbers into the calculator, but understand that D is the only set of 3 side lengths that could actually create a right triangle. Now let's continue on, putting the Pythagorean theorem back into some more context. 13 says one of the diagonals of a rectangle measures 15 centimeters. The width of the rectangle is 6. Determine the perimeter of the rectangle. Notice we did something very similar in number 11, but we found the area of the rectangle. Remember, perimeter is the total distance around a shape. So we have to find all the measures that represent the outside of the shape. And we're given the length of the width and the length of the diagonal. So I'll just kind of sketch that, kind of represent what we're drawing or what we're finding here. One of the diagonals is 15. So we have this diagonal here, and the width is 6. And so if we're going to find the perimeter, we definitely have to find this measure here or this measure. Knowing it's a rectangle, these two sides are actually the same length. So we definitely need to find the length of our rectangle. Well, as long as we know that 15, the diagonal, is actually the hypotenuse of this right triangle, we're going to plug in 15 for C. So we'll plug in 6 for A. We'll say we're solving for B and plug in 15 for C. So hopefully we found that B squared is 189. So B is equal to the square root of 189. So if you're taking a moment to try to figure out the largest perfect square factor, or possibly doing the factor tree, you should get, writing with the eraser that won't work, you should get that 9 times 21, 9 is actually our largest perfect square factor of 189, because 9 times 21 is 189. So we'll take the square root of 9 and get 3. And then because 21 is not a perfect square, we will leave 21 underneath the square root. So we have the length of our rectangle to be 3 times the square root of 21. Well, if we know that this width is 6, this also has to be 6. And if this length is 3 times the square root of 21, this will also be 3 times the square root of 21. So before I show you this math here, I first want to ask, can you add 3 plus x? And some of you, dare I say, will tell me, yes, you get 3x. But no, no, no. I ask, can you add 3 plus x? You can't actually add 3 plus x. You can multiply 3 times x or show that you want to, and you can show that you want to add 3 plus x, but you can't actually add these two because they're unlike terms. And variables and radicals work very, very similarly. So we can, in fact, add 6 plus 6 and get 12. And we can, in fact, add 3 times the square root of 21 plus 3 times the square root of 21. Or actually, just like if I said, what's 3x plus 3x? Hopefully you would say 6x. You actually didn't do anything to the x. You just added the coefficient, the number in front of it. So in the same way, adding 3 times the square root of 21 plus 3 times the square root of 21, we get 6 times the square root of 21. And because this term has a square root of 21 and this one doesn't, that's as simplified as we can say is the perimeter of our rectangle. So we'll say 12 plus 6 times the square root of 21 centimeters. Remember, it's not squared here because we are not dealing with area. Now, item 14, most of us know some properties of a rectangle, a square. Item 14, we didn't actually take the time here to look at the properties of a rhombus. So you can actually omit number 14. But I'll kind of fill you in for those that kind of want to learn something about the rhombus, how to solve item 14. If you notice, I'm running out of room here, so I'm actually going to go all the way to the top of the page and work item 14. So it says the longer diagonal of a rhombus is 16 centimeters, implying that there's also a shorter diagonal. So it says determine the length of the shorter diagonal if the perimeter of the rhombus is 40 centimeters. So let's actually go to the top here. I'll sketch what a rhombus looks like. It's essentially a square that does not have right angles. So as I'm seeing up here, I really have no room up here at all, but we'll go as far as we can. So this diagonal, we'll call that the longer diagonal, has a length of 16 centimeters. And our task is to find the length of this shorter diagonal, given the fact that the perimeter of our rhombus is 40 centimeters. Well, a rhombus, like I said, is a square without right angles, so each side of a rhombus is congruent. So if the total distance around the rhombus is 40 centimeters, each side of a rhombus has to be 10 centimeters. Well, if you notice when I draw these two diagonals, I actually create a right angle. So there are actually 4 right triangles that make up a rhombus. And it's when these 2 diagonals intersect. So let's use a different color here. Maybe you'll be able to spot it. Use black, I guess. If we know the length of this longer diagonal is 16, then half of it is 8. So we actually now have a leg of a right triangle. So let me kind of highlight just the right triangle, if you would. So we have this leg, which is 8, a hypotenuse, which is 10. And before we can find the length of the shorter diagonal, we definitely need to find the length of this other leg. And we'll use the Pythagorean theorem to do it. So we'll call this leg B, and we'll say 8 squared, one of our legs, plus the other leg squared is equal to our hypotenuse squared. 8 squared is 64. B 10 squared is 100. Subtract 64. B squared is 36. And you might know this one. 36 is a perfect square of, hopefully you said, 6. So the length of this side is actually 6, I believe, centimeters. So just using what I kind of told you about, if the total length of this longer diagonal was 16 and we took half of it to find this leg, well, if the length of this part of the diagonal, shorter diagonal, is 6, then the total length is 12. So we're saying the shorter diagonal is 12 centimeters. So using some properties of the rhombus here, primarily focus on using the Pythagorean theorem. So we'll add that here, 12 centimeters. Now the last one, by far the most complex one, is a very interesting and definitely an end of course type of question. Item 15 says, to store his art supplies, Kyle buys a cube-shaped box with 8-inch sides. His longest paintbrush is 13.5 inches long. Explain how Kyle determined that the 13.5-inch paintbrush could fit in the box. So they're telling us it does fit in the box. So let's make sure we understand what a cube is first. So a cube is made up of 8 sides, and each of those 8 sides is a square. And they tell us that it's a cube-shaped box with 8-inch sides. So you think about it here, every single side that you see of this cube is 8 inches. Now, might sound easy enough because you're thinking, well, certainly the paintbrush couldn't lay flat here. It's 13.5 inches. But maybe we could figure out that it fits at this diagonal. Maybe I can kind of put it in at the diagonal. So let's start by finding the length of this diagonal, which would be 8 squared plus 8 squared equal the hypotenuse squared. 8 squared is 64. 64 plus 64 is 128. And we will take the square root of both sides to find out what C is. Now, 128 is not a perfect square. In fact, if you take the square root of 128, you get approximately, let's see if I can write this here, approximately 11.3. But the problem is they said that the paintbrush could fit, a 13.5-inch paintbrush could fit in the box. But how so if the length of this diagonal is roughly 11.3? Well, there's actually another diagonal because we're dealing with a 3-dimensional shape, another diagonal that's at work here. So let me see if I can draw another diagram, kind of show you the diagonal that we're going to use to fit the paintbrush in it. So you got to recall that this is a 3-dimensional object here, and I'm drawing it on a 2-dimensional plane. So this diagonal did not work. That was only 11.3 inches roughly. So we're not actually going to go on the side of our cube. We're actually going to start in one corner of the box and go to the top corner, going across that 3-dimensional plane. So we still will have a right triangle. It's just going to be a little bit unique. We know this side is going to be 8 inches. And in fact, what we just did by finding this, that's a diagonal right here, diagonal of one of our squares, that's the square root of 128 inches. So we've actually already done some of the legwork by finding the diagonal that showed that it possibly couldn't fit. So now we're going to find this diagonal across the three-dimensional plane by still using the Pythagorean theorem. So we'll take 8 squared plus the square root of 128 squared, and we'll see if this length now, this diagonal across the 3 dimensions, is in fact long enough to fit the 13.5 inch paintbrush. Now 8 squared is easy for us. We actually already did it. We found it was 64. So let's explain what math is happening here when we take the square root of 128 and square it. Let's go back to here. We said that c is equal to the square root of 128, and c squared is 128. So the square root of 128 squared is 128. This little exponent, the 2, which we call square, actually undoes the square root. They're opposite operations, just like addition is opposite of subtraction. So when you square a square root, you get that number underneath the square root, equal to c squared. 64 plus 128 is 192. And so c squared is 192. Now we're going to see what c is. So we'll take the square root of both sides. And we see that c is approximately 13.85 or 86 inches. So how could Kyle fit the paintbrush in his box? It's actually this diagonal from one corner of the box to the other corner of the box. So it's actually a diagonal across the three-dimensional plane here, which is actually very, very interesting. But notice, when we strip it away from all the complexity of the cube, we're still dealing with the Pythagorean theorem because a cube is made up of squares and a square is made up of right triangles. So just keep that in mind as you're working through these practices with the rhombus, the rectangle. We are still dealing with a right triangle when we strip it away from all the context we're looking at. Thank y'all for watching. Hope that helped.